Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants, and today we are looking at dipole moments. We're asked to predict whether the following molecules have a dipole moment, and the only way of doing that is to draw the molecule. The thing to remember regarding dipole moments is that you're looking at the difference in electronegativity between connected atoms that are atoms that are bonded together. So let's quickly draw the CO2 molecule. That shouldn't be too terrible. We'll just go ahead and do that real quick. And we got a couple lone pairs. All right, now we've got the CO2 molecule. So if you recall with electronegativity, it increases as you move up the periods, and it increases as you move down the groups. Which is to say, if you have a periodic table, it's going to go up the periods from period 7 to period 1, and then down the groups until it gets to group 8A. So that's the way electronegativity trends. Carbon and oxygen are very close together, but carbon is less electronegative than oxygen, or we can say that oxygen is more electronegative than carbon. So we're going to draw vectors to indicate the difference. Basically what's happening is the electrons are getting pulled from the carbon toward the two oxygens on either side. So we can draw vectors here, dipoles. They go from positive carbon to the more electronegative oxygen. And those dipoles are indicating that the electrons in the molecule are getting pulled to either end. But carbon dioxide is a linear molecule, and that's important to remember. And because it's linear, because the electrons are getting pulled in equal amounts in either direction, it's kind of like a tug of war, where both sides are completely equal. When both sides are completely equal, the center does not move. And when the center doesn't move, there is no dipole moment, because the vectors essentially cancel each other. Let's take a look at the next one. We have H2. Whenever you see diatomic anything, there is no dipole moment, because the electronegativity of the two hydrogens is equal. There's not even a dipole vector that you can attribute to this. It is simply a non-polar molecule. And in general, it's non-polar, not even that the poles cancel each other out. It's simply a non-polar molecule. Okay. Let's take a look at the next one. We have methane. And again, we're going to take a look at this. Carbon is more electronegative than any of the hydrogens that are attached to it. So what's going to happen is each of these dipoles are facing toward the carbon. And while you may have a slightly polar bond, ultimately, because they're all in opposition, they're all facing toward the same area, they're all doing it equally spaced apart, the result is it cancels, and just like with CO2, you have a nonpolar molecule. It's important to realize that as the dipoles cancel each other out, while you may have a polar molecule, there's no effective dipole moment, and therefore the molecule itself is nonpolar. Let's take a look at another one more, and it's going to be chlorine trifluoride. So in drawing this, we have chlorine. We have it attached, single bonded to fluorine. And each of those fluorines has 6 electrons, or 3 lone pairs. And we are short a couple of lone pairs. So we're just going to put them like so. Now, one has to recognize that fluorine is, while it is more electronegative than chlorine, so when you're drawing your vectors, your dipoles, you're going to pull them away from chlorine. But the issue comes to pass that you also have 2 sets of lone pairs. And because we have 2 sets of lone pairs, we need to show a dipole indicating that the actual moment of the dipole moment itself, is pulling the molecule toward that lone pair. They don't have anything canceling them out. So the ultimate result is that you have a dipole, and this is a T-shaped molecule. In this case. And it does have a resulting dipole, which brings stretches the molecule and makes it a polar molecule. It stretches the electrons, pulls the electrons toward that moment, and as such, you do have a polar molecule.